So in general, we can produce standing sound waves in a particular section of, let's say, a tube where air could be trapped, such as a musical instrument like a flute. And we can see that the general picture here is shown as we saw in the simulation just now, but with both ends being open to the air. So we can see that both ends are open to the atmosphere, let's say, of air outside, and therefore we can see in this blacks the black arrows the maximum displacement. This is what we refer to as S as a function of position x and t time, and so this is displacement is maximum here. So depending on whether you're looking at the snapshot of a standing wave looking at the displacement S or the change in pressure, well, here we're looking at the displacement, and we can see that displacement, we can just kind of point here, that's where it corresponds to a maximum or antinode of a standing wave. And in the middle, we are never displacing from equilibrium, and therefore we have a node. If we look at the pressure, because it's open here to the atmosphere, the change in pressure here at this section would produce a pressure node. So the change in pressure would be 0, and therefore I have a pressure node, and then the same for here at that end, as it's equal to the atmospheric pressure as well. And so it depends on which property you're looking at, pressure or displacement, so we have to keep that in mind. And we have to think about whether it's open or closed. Here we can see that this is the graph of the displacement, and it is the first for harmonic frequency or the lowest frequency, also called the fundamental frequency. And now we'll look at the other standing wave patterns that we could produce.